Right, okay, this is the phases of matter bit. It's extremely simple stuff, and you mostly all know it. I'd be surprised if any of you don't know this. But, okay, so basically, we're going to describe the kinetic model. We're going to define internal energy. We are going to describe the oscillations of Brownian motion and what they show us. And we're going to define the terms latent heat of fusion and vaporization. The only thing worth saying, really, is that the kinetic theory is a theory that all the bulk properties like pressure, volume, and temperature are described by the mass, the energies, and the speeds of small particles within the system, right? And another thing worth saying is a molecule is the smallest particle of a pure substance that is characteristic of that substance. So what that means is that when we talk about the smallest particles in kinetic theory, we mean the molecules. We're not talking about the atoms or the quarks or the protons or the neutrons. Like, we're talking about molecules as the smallest particles. Right, so solid, they're solid, right? Attractive, very close together, not a lot of kinetic energy, so they're bound in potential wells. It takes a lot of energy to get them out of their potential wells. You increase the heat to them, you increase their vibration. If you sufficiently increase their vibration, you give them enough potential to escape the little state they're in, and they go into the next state. That can be called melting, and it works like that. A liquid, they're nearly the same size, and in some systems, like particularly famously water, it actually loses volume when it becomes a liquid, and that's something to do with the hydrogen bonding. But in general, the size of a liquid isn't greater. It has no fixed shape, because all they're doing now is they're moving fast enough for that, like that rigid crystalline or whatever structure's in place to come back into effect. Yep, that's liquids, and if you give them sufficient kinetic energy, they will vaporize and they'll escape the next potential and get into the next state, which would be the vapor or gas state. Gas state is the more interesting state because that is, well, yeah, it's just a more interesting state, isn't it? Because they're now like completely defying the temptation to be near each other. So the intermolecular forces in that have become completely overcome, and now they're negligible. It's rushing around all over the place, and it's got this rapid, random motion. It collides with things, and that collision and transfer of momentum is what gives rise to gas pressure. They're about 10 times further apart than they are in liquids and solids, and they can be heated up and it'll make them move faster, just like the other stuff. They can move into the fourth state, which is the plasma state, and this is probably the easiest one to get your head around in terms of a state change, even though it's like the most weird state, because we can actually really clearly say the amount of energy required to ionize them is a known quantum amount of energy. So plasma is basically just take a gas, heat it up so much that the kinetic energies around them make it impossible for the bound electrons to stay attached because it's just moving around so much. The action of the force and the sudden rates of change of momentum is sufficient work to provide the minimum energy to strip electrons off. So it becomes ionized. Then it becomes like a material that's electrically charged and dipolar in like an entire system of dispersed charges. So it can be affected by electric and magnetic fields, and it even has like a wave motion within its entire body because of the interactions of positive and negative charges that can't reattach each other because they're just going whoa like that. It's all chaos. Funnily enough, it is the most common form of matter because it makes up stars and hot nebula. Right, Brownian motion. So Brownian motion, I'm sure we've all heard of. It's basically Scottish guy, botanist, drops some pollen grains in some water and notice that they're moving around despite the fact that the water is perfectly still. And it took 80 years for Albert Einstein and some other guys to realise that that was a verification of the ideas of kinetic theory. So setting up a situation like this where you're looking at with a low power microscope, a laser beam shining through some smoke particles, in the same way that you might spray deodorant on the lasers to make them visible. So you know, like Mission Impossible. That you know. Yeah. So basically, you've got the smoke. It's getting whacked into by these invisible particles that we know are the molecules, and the constant movement of them and the random motion spreads out this smoke in any number of directions. What we can show directly is that the temperature of that material, or that water, makes the ink or smoke, or the temperature of the air, the temperature of whatever the substance is that's invisible here, means that this tends to spread out faster. So higher temperature, the faster it spreads out, which is an even bigger verification of the idea of the kinetic theory. What was really cool is that this here, that looks like a bad drawing of the British Isles, is totally random. There would be thousands of traces like this of what the smoke was doing, and it was absolutely unpredictable. Each time it was totally something new. Telling us a lot about the size of the particles as well. There must have been really small because they're invisible, absolutely loads of them because the number of constant changes was really large, too large to be done by a single particle, and the fact that it's completely random indicates that it can't just be a single particle, because then it would be very predictable. So it's very many particles. Yes, pressure exerted by a gas. So pressure exerted on a surface is defined as the perpendicular force per unit area of the surface, or we could consider it the rate of change of momentum per unit area, right? Because we know that rate of change of momentum is the definition of force from Newton's second law. So consider a gas molecule smacking into the surface of its container and then being bounced off in a different direction. Now we all know that whenever a thing goes through a change of something measurable and vectored, that it takes force, right? So it's gone through a force, it has gone through a change of momentum, so there must have been a force. And if that happens in a relatively short time frame, then we know that that force is large. And so we can explain the idea of these balls being able to produce pressure, these gases, these particles being able to produce pressure because of the collisions, because there's so many of them and they're moving so fast. And that whacking in and transfer of momentum means that the wall itself has experienced a force just like the particles experience a force, and that force is outward, which gives rise to the idea of an internal pressure matching what's outside. Okay, energy of a substance then. The internal energy of an object is the sum of the random distribution of kinetic and potential energies of all its molecules. If you were to take a single molecule and know its kinetic energy and know its potential energy, and then you would do that to every single particle within a substance, and you'd know its internal energy, right? You can increase that internal energy by doing work on the object, heating the object, or through the action of EM waves, like, you know, all that quantum jazz. So if you haven't done the quantum stuff now, because you're doing Unit 5 first, then it's just like a heating effect from EM waves, really. Okay, so heat energy is the energy transferred between 2 points as a result of a temperature difference between them, or it's also called thermal energy. Kinetic energy is the component which is due to the vibration of the molecules about their fixed positions and depends on the temperature. Obviously, when you talk about fixed positions, that's a bit nuts in a gas or a liquid, really, but it's about their vibration. Or it could just be the actual molecular speed in a gas. And the potential energy is the component which is due to the attraction forces which hold the molecules together. Mainly in the substances that we're going to be talking about, it's van der Waals. It depends on the size of the bonding forces as well as the separation of the nucleus. So, for example, I can heat up something, and supplying them with heat causes an increase in the kinetic energy of the molecules, or I can push the piston down, reducing the volume in which the air is contained, and I have created an increase in the potential energy of the molecules, and really, I've probably increased the kinetic energy as well, because I've increased the pressure and reduced the volume. I must have increased the temperature. It's just inevitable. There's no way I could have not done it. Right, so the ideal gas, this is what we're here for, right? So in the case of an ideal gas, the intermolecular forces are assumed to be negligible, and so the internal energy is entirely due to the random kinetic energy of the molecules. We're ignoring potentials here because it's just too small. For real gases, there are obviously small finite forces, and potential energy is a component, but it's minor, even in a real gas. Helium is probably the most comparable to an ideal gas because it has basically no van der Waals attraction or any level of attraction between itself, and it's generally inert as well, so that's another nice thing. Right, now what we're going to do is consider melting or phase changes in terms of the kinetic model. So let's think. When you heat up a substance, its temperature rises until it reaches a particular value called the melting point, and it'll start to change from solid to liquid. Even though it's been heated up during that period, the temperature of the substance doesn't change, and that's while it's melting. Once the melting process is complete, the temperature will rise again, and it will reach the value called the boiling point, at which point it starts to boil again. Even though the substance continues to be supplied with heat, its temperature will not change until all the liquid has changed into gas, after which time it can start to rise again. Right? Now let's think about that microscopically. Heating a solid causes the molecule to gain kinetic energy and vibrate more vigorously. At the melting point, the molecules have gained enough kinetic energy to break the bonds which hold them together. Heat energy is being used to break bonds, hence no change in kinetic energy and no change in temperature. The molecules then take on a more disordered arrangement, and their potential energy is increased by the fact that they're slightly further apart. And then continued heating increases the disorder, spacing, and speed of the molecules, which means that both the kinetic and potential is increased. While ever there's a rise in kinetic, there will be a rise in temp. Eventually, at the boiling point, they've got to use up all that heat energy that's been constantly poured into it to overcome another potential well. So there'll stop being changes in temp during that phase. Right? And we need to know and be aware that temperature is simply a measure of kinetic energy of a substance. And we'll show that again at another point. So, for example, during a phase change, there's a constant sort of source of heat energy, but the temperature is not rising. So we can relate heat and temperature. They're usually some level of proportional except during a phase change. So some points to note there. During a change of state, energy must be supplied or extracted, temperature stays the same, and molecules are breaking free of each other. When I say extracted, we forget that we can go back through the states as well. So if I'm going from a liquid to a solid, I need to radiate energy out. I need to cool down. And in between the changes of state, energy supplied creates a change in temperature. And the molecules will move faster or slower. So look at this graph. This is water under constant heating. And AB describes heating the substance resulting in measurable changes in kinetic energy. BC is producing no measurable changes in kinetic energy, and so it's all going into a phase change. BC is a melting phase change. CD is in the liquid phase. You'll notice that there are changes in the gradient. That's important to note as well. Greater heating doesn't always result in the same changes of temperature. In different phases, it's harder or easier. But in CD, all the heat is going into making kinetic energy. So there is measurable changes in EK. Once again, when we get to the DE phase, we get to a phase change again. And there's no rise in temperature despite continued heating. That's because of all the energy is going into a phase change. And then E and F, it's heating up again, resulting in kinetic energy gains.